Okay, ladies and gentlemen, welcome to the video notes for Chapter 10, Section 5, which is entitled Tangents, but really more specifically should be entitled Tangent Lines, as it discusses a new form, a new definition for the word tangent, and how that applies to circles. So these video notes are going to cover Section 10.5 in your book. That might be a little bit quick, but it's a video. You can always rewind and re-listen to stuff. So here we go. We'll start off with the actual alternate definition of the word tangent, or tangent line would be a more specific way to phrase it. It is called it's a coplanar line that intersects the circle at exactly one point. This point is known as the point of tangency. So in the figure there, we have a line AB, which we would say is tangent to circle C at point A. It only intersects the circle at point A. Nowhere else, there are no other points that those two items, the line and the circle, have in common. So again, A is the point of tangency. Now, how are we going to get into this? Well, mostly we're going to be dealing with situations with only one circle. It is technically possible that the same line could be tangent to multiple circles, in which case it would be known as a common tangent, which is a line, ray, or segment. A line, a ray, or a segment that is tangent to two coplanar circles. I've got a couple of visual examples there at the bottom of the screen. So, we're going to be dealing with basically two rules in this section. The first rule is Theorem 10.10 in your book. It says in a plane, a line is tangent to a circle if and only if, so there's that biconditional statement, meaning that both the theorem and its converse are true, if and only if it is perpendicular to a radius drawn to the point of tangency. In other words, line L is tangent, if it's tangent to circle S, then L is perpendicular to ST, and if L is perpendicular to ST, then L is tangent to circle S. That's what we mean by if and only if. It means both of those statements are true. So in other words, if line L in this picture is tangent to the circle, we will always have a boxy here. That will always be a 90-degree angle, which is going to be key to what we're doing. Okay? So we're going to look at a couple of different applications of this rule going in both directions. We'll start with the showing that a line is tangent to a circle. Okay? So in the example here, JL is a radius of circle J. That means L lies on the circle. Notice that JL is listed as being 8 units long in the picture. It says determine whether KL is tangent to circle J. Now the way that we justify our answer is we show our work. So in order for this to be a tangent line, we need to show whether or not angle JLK is a right angle. So that requires us to come up in our heads with some theorem that would allow us to figure out whether or not the side lengths of the triangle JKL could be a right triangle where L is the right angle. Well, in that case, KJ would be our hypotenuse. However, you'll notice that there's a trick to this. The 9 is only that distance. That is the 9. It's from K to the circle. So the rest of this is the radius, which is 8. And we would have to add those together to get the KJ. 9 plus 8 would be 17. So what we do is we check the Pythagorean theorem. The Pythagorean theorem would be 8 squared plus 15 squared, and we're checking to see whether or not that is equal to the hypotenuse 17 squared. So we run the check here on the Pythagorean theorem, and if it's true, the answer to this question is yes, KL is tangent to circle J. And if it's not true, if that fails, then it's no. So 8 squared is 64, 15 squared is 225. We're checking to see if those add together to be 17 squared, which is 289. And in fact, They are equal. So this does work, which means the answer is yes. Because if this is true, then L has to be a right angle, which means KL, it says, so we've proven here that angle JLK is a right angle, which, according to our rule, means KL is tangent to circle J. Okay? So the next example is for you to try. Please pause the video and try it on your own, and then resume the video and see how you did. Again, that's that top example there. Pause the video and try it. Okay, so same sort of idea. We're going to check the Pythagorean theorem to see if G is a right angle. GF is 6, so is the distance from F to the circle. That is 6, which means the entire length of HF is 18 units. So your Pythagorean theorem that you should be checking is 6 squared plus 8 squared to see if it is equal to 18 squared. And hopefully by this point in the year we're comfortable enough with our perfect squares to recognize immediately that that is not going to work. Okay, 36 plus 64 is definitely not equal to 324. So this failure means that angle HGF is not a right angle, which means the answer to this question is no, because if G is not a right angle, then HG is not tangent to the circle. Okay, so now we're going to go the other direction. So this time they've told us that JH is tangent to circle G. Now what that tells us, this part right here, JH is tangent to circle G, what that tells us is that angle J in the triangle must be a right angle. Now ask, what is the radius of circle G? Well, we don't know what that radius is, so we use the value we always use when we don't know something, and that is a variable x. Now notice that I labeled both GJ and GK with an x, because that is the 8 is only the distance from K to H, and we don't know the rest of this distance. So the big thing here, the big trick to this problem is remembering that when we add x and 8 together, we get the quantity x plus 8. Then we need some sort of equation that will allow us to solve for x. Well, that would be the Pythagorean theorem again. X squared plus 12 squared equals the quantity x plus 8 squared. And your algebra teachers will be absolutely furious with me if I am not extremely careful with how I teach this next step. Now the left side of that equation is simple. X squared is x squared. 12 squared is 144. It's the right side of the equation where many students will make mistakes. They will try to say that x plus 8, quantity squared, is x squared plus 64. That is incorrect. Remember that this notation of squared means that we are taking that binomial and we are multiplying it by itself, which means we have to reach back into our basic algebra skills and we have to FOIL here, or double distribute, whichever phrase your teacher used. We have to do x times x, which is x squared, x times 8, which is 8x, 8 times x, which is 8x, and 8 times 8, which is 64. So notice if you just square the first and last terms, you're missing the 2 8x's, which means your answer is wrong because you're missing the middle term of this new trinomial, 16x, because we add 8x and 8x together. Those are like terms, so this is like side work, okay? So what we know is that x plus 8 quantity squared is x squared plus 16x plus 64. Now we're going to continue to solve the equation from there. When we subtract x squared, it drops out of the equation entirely, which is super nice. It saves us lots of energy. 64 needs to be moved as well so that x is isolated. And that gives us 80 equals 16x. So then we divide by 16, and we get x equals 5. Okay, so that leaves us with two more examples of this type of problem on the next page. I would like you to pause the video and try these two examples on the next page, then resume the video and see how you did. Okay, in 3a, there's no trick to this. It's pretty straightforward. We're supposed to find the value of x, and it tells us to assume that any segment that appears to be tangent is tangent, which means we're supposed to realize that angle C in the triangle is a right angle. Set up the Pythagorean theorem, x squared plus 14 squared equals 17 squared. Now this is way easier than the last example because there's no binomial to square. We just have to work through our perfect squares. 14 squared is 196, 17 squared is 289. We would then subtract 196 from each side, which would give us x squared is 93. Now, to get rid of the squared, we take the square root. Now, depending on your teacher, depending on what the directions say, which in this case they do not specify, we might be able to leave the answer as the root of square root of 93, which does not reduce. However, if it says to round to any specific value, that is approximately 9.64. We'll go to the nearest hundredth, okay? But I really would be looking for this exact answer because there's no reason to turn it into a decimal. That's just one more step where we could make a mistake if the directions don't specify. Okay, on the second example here, this is another one like the one on the previous page. We have to realize that QR is x, and that RS in its entirety is the quantity x plus 2. So, we set up our Pythagorean theorem. X squared plus 4 squared equals quantity x plus 2 squared. And then once again we have to be careful. Okay, x squared plus 16 equals, and then on the other side we have to FOIL x plus 2 times x plus 2. Well, x times x is x squared, x times 2 is 2x, 2 times x is another 2x, and 2 times 2 is 4. Combine like terms, we're looking at x squared plus 4x plus 4. So the right side of our equation should be that, x squared plus 4x plus 4. Then we solve. Now again, just like that last example, when we subtract x squared from each side, it drops out, which saves us a lot of time and energy. We subtract 4 from each side, and we get 12 equals 4x, and then we divide by 4 to get x by itself, and we get our answer of x equals 3. So those are the applications of our first tangent rule, which is by far the hardest of the two. Okay, on to our second rule, which is, if two segments from the same exterior point are tangent to a circle, then they must be congruent. Okay, so what we're saying there is that if segment AB and segment CB are tangent, then that means that their lengths are equal because they are congruent segments. Notice my markings. So pretty straightforward here. In the directions for the example, it says AB and CB are both tangent to circle D. That means they have to be congruent. So if AB is congruent to CD, or CB, then that means that their lengths are equal. So all we have to do is set x plus 15 equal to 2x minus 5 and solve that equation to find the value of x. So that would involve getting the x on one side and getting the number on the other. So we have to subtract x from each side and add 5 to each side, which gives us 20 equals x. Really straightforward. Should be relatively simple most of the time. So again, please pause the video and try examples 4a and 4b, and then resume the video to see how you did. So again, it's the directions say find the value of x. Assume that any segment that appears to be tangent is tangent. So in the picture, RQ and RS, we assume to be tangent, which means they have to be congruent. So our equation should be 3x plus 8 equals 26. Subtract 8 from each side. Gives us 3x equals 18. Divide by 3. And we get our answer. X is 6. In 4b, same idea. Wx and xy are both assumed to be tangent because they appear tangent, which means they must be congruent. So 3x plus 6 equals 2x plus 9, and we solve that equation. We subtract 2x from each side and subtract 6 from each side. That gives us x equals 3. So that's the easy version. Now the more advanced version of this involves inscribing a circle into a polygon, or circumscribing a polygon around a circle. So here we have a graphic design word problem, which is essentially we've taken a circle and placed it and inscribed it into the triangle, meaning that triangle ABC is circumscribed around circle G. The problem asks us to find the perimeter of the triangle. So to do that, find the perimeter, we need to add up the side lengths, which means we need to know all of the side lengths. So we use this property that we've got from the rule. Point A is an exterior point where two tangents are intersecting. So AD and AE are equal, are congruent, which means AE is 8 feet. Okay, now finding CD is a little bit tougher. We have to think our way through this. Okay, if EB is tangent to the circle and BF is tangent to the circle, then they're equal lengths, which means BF is 7 feet, which means that CF would be 10 minus 7, or 3 feet. And if CF is 3 feet, it is congruent to CD, which makes CD 3 feet. So the big thing here is we can get lost in the adding up of the sides. What I would suggest is that you find the length of each side first. 8 plus 3 is 11 feet for the total length of that side. And 8 plus 7 is 15 feet for that entire side. And then we already have 10 feet for the length of the third side. So the perimeter of the triangle is the sum of those three side lengths. 11 plus 15 plus 10 is 36 feet. Again, there's one more example here. It is a little bit different. You need to set up and solve an equation for x, but the setup is the same idea. So please pause the video and try the last example, and then resume the video to see how you did. Again, I'm referring to this example here. So pause the video, try it, and then resume the video and see how you did. So, same idea here. We've got 4 points. The quadrilateral is circumscribed around the circle, which means these are all tangents to the circle. We've got these 4 points of tangency for all these different lines. Okay? So if AT is x, so is TB. If UC is x, so is BU. If DR is 3, CR has to be 3. If AS is 3, SD has to be 3. So again, we need to add up all of those lengths all the way around. X, 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 and then 4 3s as well. And that would equal the perimeter, which is given in the problem as being 18. So we should end up, when we combine like terms, with 4x plus 12 equals 18. Subtract 12 from each side. Gives us 4x equals 6. And then divide by 4, which gives us x is 6/4, which reduces to 3/2. Or I would accept the very nice decimal 1.5. That does it for this section. Thank you very much for your time and attention.